right, so, whoops, I better pull my microphone. So we're going to start a unit on isomers. I mean, not start a unit, but we're going to look at isomers in our organic unit here because organic compounds have many isomers, or they can have many. So, first of all, let's talk about what isomers are. Isomers are things that have the same formula, but different arrangements and usually different properties. So we've looked at structural or constitutional isomers before. For example, we looked at butane and 2-methyl-pentane as two possible structural isomers for C4H10. And we could do that for many, many others. And then there's stereoisomerism. Okay, that's the same, it's the same formula and the same bonds, but those bonds are arranged differently from each other. And there are two types of stereoisomerism, and that's optical and geometric. Okay, so we're going to consider structural isomerism. I just did that. So structural isomers are the ones with the same formulas but different chemical properties. So you can have the straight chain and then shorter chains with substituents on them. Now I want to talk, though, about molecules that are chiral. So I want to talk about tetrahedral molecules. All right, so here's our tripod with the camera on it. It has a sort of a brown, a red, a green, and a yellow sort of molecule on them. And sometimes these can be chiral, and chiral means they're not symmetrical. And we'll come back to optical isomers in a minute, but chiral means they aren't symmetrical. So what that means is that they don't, that they're mirror images of each other. So like my hand, okay, my hands, your feet, they look alike when you're looking straight at them, but try putting your hands on top of each other, or try putting your left foot in your right shoe. There is a difference, and that's called optical. Okay, so we can see it looks the same, but it's not. So let's look at this same let's look at this same tetrahedral center, all right, which is what I want to look at and we're going to try to make these look exactly the same. If we can make them look exactly the same, then they're identical. If we can't get them to be the same, then they are going to be asymmetrical and optical. All right, so in this case, we have our central blue atom. Again, we have the brown and the brown on the top, and we have a red and a red over here in that same plane. Now, in this one, the green one is coming out toward you and me, but in this one, the green one is going back. And no matter how I turn this molecule, I'm never going to be able to set these exactly like this one because it's a different molecule. Okay, so we call that chiral on a tetrahedral center. And so let's look at what chiral means. All right, chiral means that there are four different groups bonded on a central atom, just to one atom. So if we take CH4, for example, we know how to draw that over and over by now. There's its structure. Well, it has four of the same things attached to this carbon. and therefore it is not chiral, not chiral. If we take a different atom, say H with 2 or 3 BRs, I'll put 3 on here. All right, again, this is not chiral. It has 2 of the same atoms bonded to it. So we have to have 2 or 4 different groups, so that's not chiral. But here's a molecule that is chiral. Here's the carbon that we're interested in. And at that carbon, it's attached to an OH group, it's attached to a methyl group, it's got a hydrogen group, and it's got an ethyl group. This carbon is chiral. So that one is. It has 4 different things attached to it. What about this funky looking thing? Now, is this carbon right here chiral? No, it has 3 hydrogens attached to it. But let's look at this carbon. Okay, this carbon actually is chiral because it has on this side a methyl. It's bonded to a propyl type of thing. It's not really, but I'll name it in a minute. And then this is ethyl, or a 2-carbon. And right here, the last thing is just the hydrogen atom. Okay, so this carbon is chiral. Now, in reality, these are not how you name these, right? We name these according to the shortest possible numbering and the longest continuous chain. And so our longest continuous chain is 1, 2, 3, 4, 5, 6. So in reality, this is 3-methylhexane. Methylhexane is one word. But in order to analyze the chirality, we look at each one. There's 1 carbon. Here's 2 carbons. Here's 3 carbons. And then this hydrogen is out here all by itself. That makes 4 groups. What about something like an alkene? An alkene. Can that be chiral? Well, it only has, there's 1 of the carbons. Each one of these carbons only has 3 things attached to it, bonded at all. So it can't be chiral in this sense. Okay, we're not talking about not tetrahedral anymore. So that we wouldn't be looking for chiral carbons on non-tetrahedral atoms. Another kind of isomerism that we're going to deal with and look at quite a bit are geometric isomers. Now, geometric isomers are also called cis and trans isomers. These are the same atoms, the same bonds, and different arrangements again, all right? So there's the same atoms with the same kind of bonds, but those bonds are arranged differently. When you have cis and trans geometric isomers, you have to have an alkene. An alkane. Oops. Sorry about that. You have to have an alkene. No exceptions. Nothing else will be acceptable for a cis and trans geometric isomer. Each carbon has to have 2 different groups attached to it. And then you'll see that cis means that the biggest groups are on the same side. And trans means the biggest groups are on the opposite side. And so let's look at our old friend butene. We've seen this before. And so if we have 1 butene, let's first just put in our structures with 4 carbons. 1 butene tells me that I have a double bond here, and 2 butene tells me I have a double bond here. Now, I'm going to put in the actual formulas here for a second with all the carbons. CH, CH3. Okay, and then I want to make a decision about whether or not something is cis or trans. Now, when you're deciding about cis or trans, you have an sp2 in an alkene arrangement. And that means that the atoms or the groups are 120 degrees apart. So assuming that this goes in a straight line like it must, since it's planar, I'll have about 120 and about 120 degrees here. Those are these two hydrogens I just put on carbon 1. Then on carbon 2, I'm going to put in this hydrogen, and I'll put it down here. And then I'm going to put the rest of this group up here. And so my first question is, can this be cis or trans? Just a simple, can it be cis or trans? So to make a decision about that, cut this double bond in half and look at each side separately. So on this carbon, look at this carbon and this carbon separately. This carbon, let's go to this carbon. This carbon has two different groups. It's got the hydrogen and then this 2-carbon chain. And this carbon right here has two of the same groups. It's just hydrogen. This cannot be cis or trans, because in order for it to be a cis-trans geometric isomer, you have to have two different groups bonded to each carbon. So this carbon, carbon 2, fulfilled its rule right here, its role, but carbon 1 did not. So that is not a cis or trans. Now let's come over here and look at, I'm going to change this so we can emphasize something for a minute. Let's look at the 2,2-butene, where the 2 indicates that the double bond is at the second carbon. So you'll want to just draw the part with the double bond, just the part with the double bond. And then go back and put on each side whatever the groups are. So this carbon is bonded to a hydrogen at this is carbon 2, and it's bonded to this 1 carbon group. And on this group, carbon 3, we have a hydrogen and a CH3. So the question is, first, can this be cis or trans? And when you dissect down this double bond, and you look at carbon, this carbon, this carbon 2, we'll call that carbon 2 still, it has two different groups. And when you look at carbon 3, it has two different groups. And so this can be cis or trans. The question is, does it matter that they're the same two groups on each of these carbons on the double bond? And that doesn't matter. It only matters what's happening at that carbon and what's happening at that carbon, not what the groups are, only that they're two different groups. So this could be a cis or trans molecule. Now, the way I have this one drawn, it's a cis. This is a cis, and we would name it cis-2-butene. Now, why is this cis? Cis means the same side, okay, and I'm looking for the largest groups. So what do I mean by the same side? Now I'm going to dissect along a kind of the horizontal plane on that bond, and I'm going to look to see, remember this is planar and it doesn't rotate, but so I'm going to look and see what's on each side of the horizontal bond. Well, in this case, the bigger molecules are both on the same side. Let me draw a trans for you. So instead of setting it up like I did it here, I'll put in my double bond, I'll put a hydrogen on this side, and let me put the hydrogen down on that side. And then we'll put in our methyl groups, our one carbon group here. Now, when you look through the horizontal plane there, you can see that the two big groups are diagonal to each other. So this one is trans 2-butene. So trans means that there are the biggest things are diagonal to each other. Let me see. So I put this in the book to help you see. There's two things to do. First, you cut the bond in half when you're deciding if it's cis or trans. Cis or just to decide, can it be cis or trans? Can be. Can it be? It can only be cis or trans if there's two different things on each carbon, two different groups on each carbon. That's how you decide if it can be cis or trans. Now you decide if it is cis or trans by looking down the horizontal bond, and you look to see which side the biggest groups are on. In this case, the biggest groups are on the same side, and in this case, they're on opposite sides of your horizontal view. So let's decide if these can be cis or trans. This means we have to draw. So 2-methyl-1-butene. Now the 1 indicates that I'm going to have a double bond at the carbon 1, and I've got 4 carbons, so let me put that in. And then the substituent is at carbon 2, so CH3 would go right there. And then let me fill in the hydrogens otherwise. So I'll have to have 2 hydrogens here to make that carbon have 4 bonds. I'll have to have 1 more hydrogen there, 2 hydrogens here, and 3 hydrogens there. And now I want to know, can it be cis or trans? And so we could redraw this if we wanted to, where we could say, okay, this CH3, I made a mistake. CH, and then I said CH2, CH3. What is wrong with that structure? This carbon has 5 bonds. This is not a good structure. So I made a mistake. Oh, I know you love it when I do that. Let me take out this hydrogen right here. That's not proper. So we'll have a carbon and then that. Now we have 4 bonds to that carbon. And now what I was trying to say is I could redraw this. Thank goodness I did draw it. So I can decide if it can be cis or trans. All right, so I know that everything is 120 degrees in a double bond, so from here to here is 120, from here to here 120, etc. Now, can this be cis or trans? And the answer is no, because this carbon has 2 of the same things on it. 2 of the same things on it, so that won't work. Let me draw then 2-methyl-2-butene. So 1, 2, 3, 4. I'm told the double bond is at carbon 2, and I'm also told that this has to be a substituent up here at CH3. And so this will be CH3, CH, or anyway. The point is I have 4 bonds on carbon 2, so I'm happy there. I will need a hydrogen here, and then 2 H's there. Now I want to know, can this be cis or trans? Well, I don't want to redraw because I don't like to draw more than I have to, believe it or not. So I'm going to break this bond, and I'm going to look on each side. And this side has a hydrogen, and a methyl group, CH3. So that one would be okay as cis or trans, but what about this carbon? It has two 1-carbon groups on it, and so this is also not cis or trans. Now, we can just eliminate from here. Can anything that's butane be a cis or trans? And the answer is no. It has to be an ene at a minimum. It has to at least be a double bonded ene. So we could just say no on if we were looking through our answers. And we could also say no to this because butane is singly bonded. Butane is triple bonded, and we know cis and trans have to be double bonded, at least for our purposes. So what about if we draw cis 3-heptene. Cis 3-heptene. Well, let's start by putting in our simple straight lines for a minute, our chain. 1, 2, 3, 4, 5, 6, 7. Heptene means 7. And I'm told that carbon 3 has the double bond, so I'll put my double bond there. Now, I'm going to make a decision about whether or not, or what cis would be. Okay? And so I'm going to need to fill in some stuff here. And I'll put an H here, and let's put an H here. And then, of course, these will all have their hydrogens attached to. And so, have I drawn a cis or trans? And the answer is no, not really. All I've got is this straight line right now. So let me draw a cis. Okay, a cis means that the bigger parts are on the same side. Well, and I want to focus, I'm going to start with a double bond. So at the double bond, at a 120-degree angle, I can see that I have a CH2, CH3 bonded one place, and a hydrogen bonded on the other side. Now, all of that part of that chain is bonded. And then I want to get things on the same side, which means I want the biggest stuff on the same side. So all of this is going to be biggest compared to the hydrogen, so I'll put that up on the top here and put the hydrogen down here. And so this is cis 3-pentene. Could I have drawn it like this and still gotten the same thing? And the answer is yes. I mean, it doesn't matter whether you draw the cis up or down, as long as they're on the horizontal line, horizontal plane look on the same side of the carbons, same side of the double bond. So that would be a cis 3-heptene. So you start with first start by writing out the straight chain. Then put in the double bond and fill in around that double bond with all of the parts. Now you might be asking yourself, but no, I guess you wouldn't. No, not yet. Not quite where I want to be. So I could also draw a trans. Let's just draw a trans just so you can see it. In this case, I have to have the big things on the opposite side. So CH3, CH2. The big things are on the opposite sides of the double bond. And so I'll fill in my hydrogen here. And this would be trans 3-heptene. Now I have one more point I want to make, but I don't seem to have made myself I didn't seem to make myself a note. So I want to make a point though. Let's assume that you have a molecule like so. Now, you're trying to decide, what is this going to be? 1, 2, 3, 4, 5. Okay, so this is a 2-pentene. It's 5 carbons long. You're trying to decide if this can be cis or trans. And you're wondering, well, I've got, let's just pay attention to this carbon for just a minute. This carbon is bonded to a carbon, and that and the carbon is also bonded to another carbon. And so can this be cis or trans? And the answer is yes, because I consider everything in that bond and everything in this group to be part of the group that it's attached to. It's not just bonded to carbon. Here it's bonded to 2 carbons, and here it's bonded to just 1 carbon. So it's more than just what exactly it's bonded to. It's the entire group that counts on whether or not this could be cis or trans. And in this case, this one would be, as a matter of fact, trans, and without the substituent. Let's do it without the substituent first. This would be trans 2-pentene with 5 carbons. 1, 2, 3, 4, 5. However, we have a substituent down here, which makes life a little bit more difficult. Can't name it straight up that way. But in this case, we have a 3-methyl trans 2-butene. All right, so I indicated where my methyl group was on that pentene molecule. And then finally, there's a little bit more on optical isomers. Now, I said optical isomers mean that they're non-superimposable mirror images, like my hands, like your feet. Okay, they look the same when you're looking at them, but try to put a glove on your left hand when it should be on your right. Okay, that's a mirror image, a non-superimposable mirror images. Those are also going to be chiral. All right, now we only looked at chiral when there was a tetrahedral center, but there's more. That's just the simple one. So it's going to be chiral if it's an optical isomer. And these are called enantiomers. And so outside of the laboratory, you can't tell any difference in the molecules except for the way that they rotate light. Okay, one's called D and one's called L, to the left and to the right. But in a human body, or in a living system, I mean, those optical isomers that don't seem to be different when they're outside of a real situation actually are hugely important, because the way they fit together into an enzyme or your DNA or any other arrangement makes a difference in life, not in the lab. Anyway, so an optical isomer, I just want to show you this illustration for a minute. So here we have a mirror. It looks just the same. On this side we have the brown, green, white, blue. Brown, green, blue, and white. And so they look just the same on each side of the mirror. So the brown is right here in front, the green's on the top, and the white's down here at the bottom, and the blue is in the plane. Okay, so they look just the same in the when they're looking in the mirror. But let's turn it around. Now I've rotated, I'm going to rotate this whole thing 180 degrees. And so now it's turned. Now I have it looking in the same direction. So the brown is going in the same direction now. And the blue is out here in the plane. But what's happened here? These are not the same. And these are not the same. And so those are not, come back here, I thought I had another one. And so these cannot be superimposed, and therefore they're optical isomers. Optical isomers.